was looking at the Arrhenius acid-base definitions. At least that's what I think I saw. And actually, I think I saw the next step. But our Arrhenius definitions of acid and base, when you add it to water, if the hydrogen ion goes up, it's an acid. If you add your substance to water and the hydroxide ion goes up, it's a base. Right? That's your definition. Right? The one thing I do want to address, just to make sure we're careful with it, is defining your base around hydroxide. Right? So if we look at that, we'd say, oh, there's hydroxide there. New compound, is there hydroxide there? No. To be hydroxide, it must be negatively charged, which means it must be in an ionic compound. CH3OH is not ionic. Right? If it's not ionic, it's not hydroxide. That changes the chemistry drastically. And for those of you that don't think that's the case, if we ate sodium metal, we would die rather explosively and painfully. Right? If we instead eat sodium ion, we actually live. Okay? And not just live, we are required to consume sodium ion for our muscles to function. So changing the charge or the balance of electrons on an individual atom makes a huge difference in the chemistry of the molecule.
So I just read somewhere that salt gives brain damage. Is that not true? Because is it necessary to have sodium ion as an electrolyte, or can you have other ions?
You are required to have sodium ions as an electrolyte. Okay? So when we talk about the harmful effects of all of our chemicals, one of the big things that rarely directly gets mentioned in those is the quantity that causes the toxin. Okay? Everything will kill you. Even water will kill you. Okay? You can drown. That's an overconsumption of water. Okay? You can also literally drink too much water and cause your brain to swell enough that you get brain damage. Okay? So it's all about the quantity behind these things. So in an article saying that salt, what did it do? Just brain damage?
Yeah.
It probably has to do with the quantity of the salt. And the next part of that is what salt. Are they referring to sodium chloride? Are they referring to potassium chloride? Are they referring to bromides? Are they referring to iodides? Okay? Each of those is going to have their own different response. All of those are salts. So we have to be very careful about using vague terms. Okay? Very typically the word salt is being associated with sodium chloride as a general trend, but all of them are salts, so we have to be a little bit careful when we see big statements like that. The other thing, those big statements are usually being made as scare tactics. You have to take them with a grain of salt. Sorry. Okay, so be careful with that. So my opinion is the Arrhenius definition is largely useless because I'm an organic chemist, and organic chemists do things with organic materials. So we tend to... Oh, okay. Were we able to find them?
Yeah.
Okay, cool. So you can worry about passing them back then. So organic chemists tend to deal with stuff not in water, and so we don't like using these definitions because water tends to ruin most organic chemistry reactions. Okay, so we tend to pick other definitions. Okay, the other reason why these definitions tend to be a little bit weak is since they only work in water, they aren't very broad. They can't be applied out to multiple compounds. So we encounter a second definition, and this was come up with Bronsted-Lowry. And what they went through and did is changed how we defined our acids and bases. Okay. The definition still must apply to the Arrhenius definitions, but they just changed the perspective on it. The perspective they chose was saying take hydrogen ion as the base to define everything, and the base I mean core. So an acid is a hydrogen ion donor. So hydrogen ion being H+. So if I take a look at HCl, and I add that to water, I form H plus and Cl minus. Okay? H plus is there. If I run a chemical reaction, here's my HCl. What did it do in the course of the reaction? So I go from HCl to sodium chloride. Where did the hydrogen go that was attached to HCl? Is it there anymore? No. What did that species, HCl, do with the hydrogen? It donated it to the NH2. Okay? So our Bronsted-Lowry definition kind of sticks to the same core, except now instead of increasing hydrogen ions in water, it's just hydrogen ions are being transferred from your acid to some other species. Okay? What happens with the base? Instead of dealing with hydroxide, what we'll go through and do is look at hydrogen ion again. Except in this case, I'm going to refer to the base's ability to react with that hydrogen ion. What did NH2 do with the hydrogen? It accepted the hydrogen. Right? So this very subtle change in the definition allows me to apply these definitions to a much larger swath of chemical reactions, which then makes them more useful. Okay? Because the scantrons are going around, there's two people that are going to have a hard time reading their scantron because they filled it in pen. That's a bit problematic. Okay? Back to the lecture. Hydrogen ion acceptor is now a base. These definitions are a little bit broader, allow us to manipulate and understand what's going a little bit better. Okay? Are there still other definitions? Yes, we can go even broader out to the Lewis acid-base definition. The problem with the Lewis acid-base definition is it literally applies to all chemical reactions. We now have a definition that ends up being so broad that it doesn't actually help us. Right? And that's why we don't talk about the Lewis acid-base definition quite as much in 130. It might show up in 151 or 152. It shows up briefly when I teach organic chemistry, and then I back away from it to get to our narrower definitions, like acids and bases and a slightly different chemistry. Right? So ultimately, all we're trying to do is say, what are acids and bases? Since we have a fundamental idea of what our acids and bases are, what I would like you to go through and do is, given the equation shown, predict the products. Well, what do you think? Do you think we should go through that one together? Yeah? Okay, let's do that. You may regret that later, but we'll work with it. So in looking at that, we are given two reactants, SO3 minus 2 and H3O plus.
Why are there two arrows?
We'll deal with that also. It's a good observation. What do you think SO3 minus 2 is going to act as? An acid or a base? What makes an acid? Has to have a hydrogen in front. Do we have a hydrogen in front for SO3 minus 2? No. Which means it's a base. If it's a base, what has to happen to it in the course of the chemical reaction? What must it do? It has to accept a hydrogen. So what would my new structure be, or new formula? By accepting a hydrogen, am I changing the S symbol? No. Am I changing the oxygen symbol? No. Am I changing the amount of oxygen? No. What am I changing? Does that look like it has accepted a hydrogen? No. How would it accept a hydrogen? I would need to write an H. But you're saying, well, that seems awfully simple. That's the point. Okay, we're trying to address this very quickly. A base must accept a hydrogen, so we attached a hydrogen to the structure. Where does this get a little more complicated?
Double arrows.
Not even there yet. This formula is incorrect. Why is it incorrect? Okay. So we can do a couple things. Number one, it's not balanced. So what we will do with acids and base reactions is we won't balance out those two compounds. Okay. When we run an acid-base reaction, we're only going to transfer a single hydrogen, and only one. So this simplifies your formula writing, because you no longer have to go through, well, what's the charge on this one, what's the charge on this one, are those charges balanced? You just have to go through and put the atom on. However, do you still have to account for the charge? Yes. What was the charge on SO3 minus 2? Minus 2. What is the charge on a hydrogen ion? Plus 1. So when I add a plus 1 to a negative 2, the charge becomes negative 1. I would have to include that negative 1 charge in the upper right-hand corner. Right? I don't have to balance that out to make it H2SO3 minus, because what I'm looking for is just the single acid-base reaction. Okay? What else happened? Where did it get that hydrogen from? The H3O plus, which means the H3O plus is acting as an acid. If it acts as an acid, what happens to its formula? It donates a hydrogen. So what would it look like over here? H2O. What happened to the charge? Why does it lose the positive charge now? Because it got rid of a hydrogen ion. And the charge on a hydrogen ion is plus 1. So it just becomes H2. Make sense? Questions about that so far? No? Okay. So we're going to start with Nick's statement. What did you notice was different about this reaction?
There's two arrows, looks like it goes back and forth.
If we look at this reaction, we've got a new concept coming in. We have a reaction with two arrows. It goes both left to right and right to left. So when we read this left to right, we were predicting based on the reactivity of those compounds. When we go right to left, we can now go through and describe what happened to those species. So when I go from HSO3 minus, what am I going to? H3O plus? No, why not?
Because it's losing gaining the nitrogen.
That's going to be the next step. Why are you saying HSO3 minus is not H3O plus? So why are we saying it's not H3O plus? H3O plus doesn't have sulfur in it. Okay? It's the patterns. It's those shapes that you ended up doing in Greg's class last week. It's the same idea. We're just looking for the patterns. Those patterns happen to be letters. Okay? But it's still the same idea. So we're going to SO3 minus 2. What happened to HSO3 minus to look like SO3 minus 2? What's that? Okay, it lost a hydrogen. Okay. I would challenge lost as a word. We could call it donated a hydrogen. If it donated a hydrogen, what did HSO3 minus act as? An acid. What did it donate the hydrogen to? Well, what happened to the H2O? H2O became H3O plus. So what happened to it? It gained a hydrogen, or accepted a hydrogen, which means it acted as a base. So far, so good? Okay, so the next fun concept, name the base. Tell me what the base is.
H2O.
Why are you saying H2O?
It says it under it.
Because it says base written under it. Does anybody else want to be like, I challenge that. I don't think H2O is the base. Okay.
SO3 negative should be SO3 negative 2.
Why are you saying SO3 negative 2 is the base?
Says it under it.
It says it underneath it. Yes, but on the other side of the equation. Does anybody see a problem with the question? It's vague. We don't know which side of the equation we're referencing. So what we want to do, because we have a vague description, is to change that description to make it less vague. So we want to change the words associated with one side or the other to make sure it becomes less vague. Any idea what words we might change? Conjugate. What we will end up doing is adding the term conjugate. The conjugate is going to refer to the right-hand side of the equation. Sorry, Nick, for this point, but I'm going to do it anyway. Who was right, Nick or Christian? When I ask the question, identify the base. I said base, not conjugate base. So, who was right? Christian was right, because Nick said H2O. Right? Language allows us to add a layer of clarity to it so that we know which thing is which. Right? The other way that the term conjugate can get used is conjugate partners. What is water's conjugate partner in this reaction? H3O plus. So those would be referenced as conjugate partners to each other across the reaction. So we'll reference our acids and bases strictly as the reactant side of the equation, and we'll label our conjugate acids and bases on the product side of the equation, or the right-hand side of the equation. Right? We really do have to reference it as left and right and not reactant and product. Why do we have to label it as left and right and not reactant and product? Which gets back to Nick's very first observation.
Double arrows.
It's a double arrow. Because of that double arrow, both sides of the equation are reactants, both sides are products. That double arrow is referencing the concept of equilibrium, which we will see here in a second. Okay? But before we do that, are there any questions with any of that information that is written up there? Yes?
So when it says lost H, is that also referring to the donate set, or is the donate part referring to the H2?
The lost is in reference to the donate.
Okay, so it's not referring to the H2O. Okay.
No.
Okay, that makes more sense.
Okay? Another kind of language thing here. We could use lost and gain or donate and accept. Notice in the acid-base definitions I gave you, we reference donate and accept and not loss and gain. Why might we do that?
Conservation of mass. Can you confuse it because you're not losing an electron? Because it's still there forever.
It could be confused with another concept. Where have we heard the terms loss and gain before? Reduction and oxidation. So when we're referencing acids and bases, we switch the terminology to minimize the confusion between those two topics. I don't know if that's actually true or not, but it makes sense in my head. Change in the terminology, yeah. Okay? So if you guys are good with that, then let's take a minute. And you guys can write out, just like we did with the top one, this bottom equation.
So you want all that information?
I want all of that information.
And do please anchor to the language differentiation he's making there. This is an important thing.
And if you got questions, raise your hand, I'll come to you. How many of you got that answer? Nobody? You guys all said you understood the equation above, right? Didn't have any questions about it?
I actually got it. I mean, you looked at my paper.
You got this one?
Understood it. Good point.
Was that what you wrote down? Became H2SO3?
Oh, no.
I did,
Not that.
and then I crossed it off. Did you really? Because like I checked up there and like, wait, that's not it.
So I'm gonna take a wild guess that most of you wrote something along these lines.
How'd you know?
How did I know? I wonder why. How did I know?
Because He's a professional.
Who's right? You're both right. Okay. Why are you both right? Or we both right? To act as an acid, what do you need to have? You need to have a hydrogen out in front. Yes, the aqueous becomes important as far as you guys are concerned with your definitions. Don't stress about the aqueous. Okay. So you guys saw the H in front and said acid. To accept a hydrogen, what must the structure have? A negative charge. What also does HSO3 minus have? HSO3 minus is a special structure. It's a special structure because what can it do? It can accept a hydrogen or donate one. It is a molecule that is amphoteric. It can go either direction. By that same token, so can water, because water is doing the same thing in this case. Okay? So there are substances that can act as both acids and bases. Most of that is going to come from really knowing the definitions of what's happening with your acids and bases, or being explicitly told them. Okay? What I want out of this is that you guys were able to get that top equation, presumably right, where you called SO3 minus 2 the conjugate base, H3O plus the conjugate acid. Yeah? So that's good. You guys have achieved what you needed to get out of that. You were able to come up with the labeling. You were able to come up with the acids. That's fantastic. All I wanted to do was address this other concept of amphoteric in it. So that's fantastic.
So this has nothing to do with pH levels?
This has nothing to do with pH levels per se. True. Okay? So let's double back. Oh, geez. Let's double back and look at that arrow. Okay? That arrow means we have a reversible reaction, which is really dealing with the concept of equilibrium. Okay? It's the balance of a chemical reaction. This concept is so huge and important and complex that virtually all of Chem 152, second semester general chemistry, is devoted to the concept of equilibrium. So if we spend an entire semester talking about equilibrium, why are we bringing it in now? Because somebody thought it was important. I don't think it should be here, but it's part of our competencies. We got to talk about it.
It's a warm-up.
Okay? So what we're looking at is, again, the balance of reactants and products. The big extra phrase to get tied to this is the LeChatlier's principle. Okay, so what we'll do is look at some simple examples and analogies for our equilibrium and then apply LeChatlier's principle to it. LeChatlier's principle just says that reactions will always try and obtain equilibrium. They will always be balanced. Okay? So if we ask you to stand on one leg on your tippy toes, okay, you might notice, as I am, that we're wobbling a little bit. Why? Why am I wobbling? I'm not stable. I'm slightly out of balance. Okay? And what's that wobble? That's me constantly trying to attain my equilibrium. Okay? Some people are better at others than doing this and could probably just be lockstep on it. Chemistry is doing the same thing. It's constantly oscillating back and forth between reactants and products to obtain that equilibrium. Okay? If I asked you to do that and then came up and pushed you, what would happen? You would probably fall over. But since I insisted that you stay on your tippy toes, what would you do once you fell over? You would get back up and balance yourself out again. Chemistry is doing the same thing. Our reactions are obtaining this equilibrium by running. Once they are at that equilibrium, we as chemists can go in and mess with them. We can push them, laugh at them when they fall over, but then they'll get back up and reobtain that equilibrium. Okay? So, some kind of comparisons. Hopefully we aren't too old to not know what a seesaw is. Anybody knows a seesaw? Or too young? Yeah, is a common expectation. It's starting to become. Our seesaw, like playgrounds where you sit on them and they teeter-totters, the same kind of thing. Okay. They've been slowly progressing out because they're allegedly dangerous and hurt people. Yeah, we'll see. So, for a seesaw, we've got a wooden plank, and then we have a fulcrum. That fulcrum is our equilibrium. If we're looking at a seesaw, our equilibrium, we're going to put right in the middle. And then we have the two kids, and we throw our two kids on it. And the kids have a good time. Why do they have a good time? They go up and down. The plank has achieved its equilibrium, its balance, and what does the kid do? Messes with it. Right? What does the plank then attempt to do? Reobtain equilibrium. Right? So we as kids love it because we're constantly messing with the equilibrium of the system, shifting it out of balance, and it naturally wants to go back to that balance. Because it is naturally responding to that, we get to deal with that kind of back and forth. Right? That makes it fun. Chemistry is again doing the same thing. If we look at the kids now as reactants and products, okay? If I run a reaction, it will obtain an equilibrium, a balance of those reactants and products. Now as a chemist, I want to mess with it. What could I do to mess with this seesaw? Two kids on it. Okay? Remember, our kids are now reactants or products, so I don't know what the kids are. Add more reactants. If I add more reactants, what happens? Is it balanced anymore? Is it in equilibrium? No. What is the chemistry going to do to balance out? Can it just create products out of nothing and throw them in? No. Where do those products come from? From the reactants. So we've thrown more reactants in, and our chemistry will go through and say, well, I'm going to take half of that, and I'm going to convert that over to here, to products. And now what happens? We're back at balance. Okay? The equilibrium is the mathematical relationship between those two pieces. In this case, those amounts must be the same. What else could we have done to mess with it? What's that? Good point. We won't get there quite yet. That's a little more advanced. We could take away some reactant. Instead of starting with that, once we're at our equilibrium, we go through and we remove a bunch of reactant. What is the reaction going to do to reobtain the balance?
Only give you half as much product.
It's going to take some of the product that was already formed and do what with it? Convert that into reactants until we've again obtained that equilibrium. Right? Because we know reactions will always go to this balance, and that relationship is constant, we can take advantage of it and play with it to get it to do things that we want it to do. Okay? Would the reaction as shown here be a good reaction to run? We've got to know already. Why no?
It's not efficient.
Why is it not efficient?
Because you're taking away the product.
Fair enough, I accept that. Is the equilibrium shown a valid or a good reaction to run? So we have a yes. Why is it a good reaction to run?
Because now you're putting it in the same line.
Okay. If I want everybody in this class to get an A, to be a good equilibrium, what do you guys think about that being a good equilibrium right now? Is that where the equilibrium lies? Yep.
Probably not a good equilibrium.
Not a good equilibrium. Why?
I don't know, I can't really speak for myself.
Okay. If we look at the balance here, these are even. If I want everybody to be on the A side, it's not going to work. Right? I'm going to have an equal amount, not A. How could I change this equilibrium to make sure everybody was A? What's it?
One of either the reactant or the product.
Okay, so the reactant and product, good idea. I can't adjust those. Those don't get to move.
Move the equilibrium a little bit closer to the product side. So
Move the what?
equilibrium.
Move the equilibrium. What's the equilibrium? Yes.
The
Grading curve. Are you saying you're giving us a grading curve?
The triangle in between. That fulcrum. I want to move that fulcrum to adjust so that I get more products. Okay? Or more A's, so I could try and adjust a curve. Okay? That becomes entirely dishonest, and that doesn't happen. So if we adjusted the fulcrum to be all the way over here, would it be balanced right now? Would that plank be even? No. Okay? Where would it be heavily favoring or leaning right now? Towards the reactants. How would I make sure it's balanced? Put more products in. This reaction is now a favorable chemical reaction to run. Why? When I run a chemical reaction, what is my goal? To make product. Why is this one a better reaction than the first one we had drawn? I made more product. I consumed more of my reactants. So I could look at equilibrium constants and use that information to help me plan chemical reactions. If there's a chemical reaction that, say, that I want to do, I think I can get away with that. But I look at the equilibrium, and that's the information from the equilibrium, that's not going to be a good reaction to run because I'm not going to get a lot of products. Right? So I can use the information stored in the equilibrium to get me an idea of how much product I would make. The problem with this analogy is it's very static. Chemistry is not static. Remember, when I stand on my toes and try and balance, constantly wobbling. If I'm standing on one foot on my toes, would you believe me right now? I'm on one foot on my toes. Why not?
Because your legs are straight.
Am I balancing on one toe right now?
You can crouch down like that.
It's a strong toe.
That's a strong toe. Okay, would you believe it? I'm actually kind of shocked because a lot of you are going, wow, you're a Tai Chi man.
I was thinking more and figuratively,
Would you believe that I was doing that? No, why not? What would you expect me to be doing? Wobbling to attain that balance. What's happening with chemistry? It's constantly wobbling. It's constantly shuttling reactants to products and products to reactants. In the case of the fulcrum, we don't get a stat, or we see only static. We don't see an exchange back and forth. That's why we can move to the divided chamber. In the divided chamber analogy, we have reactants and products. Okay? They have a nice little division between them, and at the bottom we have a trap door. So if I'm going to run a reaction, what am I going to do? Put some stuff in there. Where am I putting stuff? On the reactant side. So I'm going to fill up the reactant chamber. Now I have all of the reactants present. What do I want those reactants to do? React to become products. So the instant I want the reaction to start, I'll remove the chamber. Okay, that trap door. What happens to the liquid? Comes down. What happens to the liquid on the other side? It increases until what happens? The liquid is equal in both chambers. Does that mean no more liquid is moving that direction and no more liquid is moving that direction? No, the liquid is still constantly moving back and forth between. The reaction hasn't stopped. It is still constantly moving back and forth. We could see this because you could take a drop of food coloring and add a drop of food coloring into one of the chambers. Eventually, the whole thing carries that color, even though they maintain the same level. Okay, so in our equilibrium, what we're saying is that the rate of the forward reaction on transitioning from reactants to products equals the rate of the reverse reaction. That's what equilibrium is. So you're still constantly running that reaction backwards and forwards. with this analogy, we still get the balance out that we got with the seesaw. Okay? I'm now at equilibrium. What could I do to mess with the equilibrium? I could put more reactant in. As I put more reactant in, that side now goes high. So what happens? It's going to drop, the product level goes up, and I obtain a new equilibrium again. Again, this time where those layers balance out. Make sense? All right, what else could I do to mess with this? So far we've done a lot of adding things. I could take out products. I could design an experiment such that I'm able to remove products. If the product layer drops down here, now what happens? It's going to rise back up while the reactant layer drops to obtain the new equilibrium. I can use this information to help me siphon products out of a reaction and constantly convert reactants across to products. It becomes a useful process to be able to manipulate individual reactions. The analogy on this one becomes a little bit harder to deal with the amounts. How would I change the equilibrium? Because in this example, reactants and products are the same concentration. I get the same amounts. How could I change the equilibrium?
Add heat to the reactant side.
So adding heat isn't a bad idea, but all heat's going to do is speed up the reaction. Which reaction? Both. Both the rate of the forward and the rate of the reverse. Since both of them are increasing, what happens? They obtain equilibrium and there's no change to the end result. Okay. How could I change the equilibrium? How could I get a different K value so the amount of reactants and products are different? In the case of the seesaw, what did I do to obtain a different equilibrium? I moved the triangle, the fulcrum. What could I change here? I could change the size of the individual chambers. Okay. Changing the trapdoor ultimately isn't going to do that much, really, and we're going to get the same result. Okay? That's going to change our favoring, say, for reactants or products. In this case, we get a heavy favoring for products because the product side is more than the reactant side. Kind of get it? So that's the analogies we're working with equilibrium. We can look at a person standing. We can look at seesaws. We can look at two divided chambers. Okay? The big part that we need to get out of this comes back to things that have now been addressed. How could I change it? Thinking about temperature. And temperature was important, but temperature changed the rate, the speed at which the reaction happened. What things might affect the speed at which a reaction happens? Because we've already addressed temperature, we can write that in here. Not to give any hints away, it's pretty low on my list. Okay. For a reaction to happen, what needs to happen? Think kind of simply. I want a chemical reaction to happen. Two things need to collide. Okay? Is there something in our everyday lives that we could consider about two things colliding? Cars.
Food in mouths.
Food in mouths, which is an interesting one. Generally, I go with couples. You're the last person on the planet. What are the odds you're going to find your partner? You are the last person on the planet. What are the odds you find a partner? Zero. Okay. There is one other person on the planet. What are the odds you find a partner? Very low. Better than zero. Okay. How could you improve the odds of finding a partner?
The surface area.
More people. So if I have more individual molecules, the more likely I will interact and find a partner. Okay? You are locked in this room by yourself, no cell phone, no internet. We still have all the people in the world. What are the odds you find a partner?
50-50. Not now.
Just gotta wait for the next class to come in.
You're the only person in the room, and you're locked in.
0.
Not very good. What changed?
You walked me in.
Okay. Something about your conditions prevented you from interacting with the rest of the world. Something was in the way. Okay. We've got all the people in the world, except now instead of them being scattered across the world, we put them all in the U.S. What are the odds of you finding a partner? They're kind of gross. What are the odds that you would find a partner? It doesn't have to be the perfect partner.
Higher.
I'm going to bet it's going to be a lot higher. You may be forced into a partnership because we may run out of space to put all the people in the U.S. Okay? So we're going to increase the odds. So we're looking at the amount of people, which is really, really important. But also to that same token, what else is important? Where are those people? So I'm looking for the relationship between an amount and the volume. What defines the amount and a volume of a substance? So we could go as far as pressure, and pressure works very well for gases because that does relate those two. Okay? But how many times are we going to run gas phase reactions? Very low, because our gas phase reactions fill whatever container they're in, which likely means they go into our lungs. That's not safe. So how could we represent the amount and the volume?
Density.
Density would work great for an individual pure substance, because I'm trying to get two different things to interact. That's not going to work.
Polarity.
Moles is an amount. When I bring moles together with volume, say a volume of liters, I end up with molarity. And molarity is concentration. By changing the concentration of the reactants, I can see an increase in the rate. More concentration, the more likely they interact. If you were locked in this room, we changed where you were located, or really the nature of how you could interact with the outside world. What we're doing is changing the nature of the reactant. Okay? What phase are you in? Okay? Surface area. If I take a log of wood and light it on fire, it takes a little while to burn, right? If I take that same log of wood and I turn it into sawdust and then light it on fire, does it burn faster? Why? Try it the other way. There's more surface area with the smaller pieces. I know which you were talking about. Right? So the nature of the reactant, that surface area, becomes super important. The phase, if I try to get two solids to interact, where can they interact?
Where they touch.
Where's that?
Where they touch.
Only where they touch. If I try and get two liquids to interact, if they dissolve, they're now entirely mixing, which means they can interact theoretically at every single molecule, not just on the outside of the surface. This is why when we run reactions, we almost always go into an aqueous phase to increase the odds that we can get things interacting with each other. Okay? We had temperature. I forget what the third one is. Third one's kind of difficult. Mechanism is referring to how does it proceed. Okay? If you're trying to find a date or look at the odds of finding a partner, on that first date, I'll give you a couple options. That first date, do you go out to dinner or do you attend one of my lectures? Why are you going to dinner?
You know, I never.
What the heck's wrong with my lecture? Doesn't have food. The balance of those changes how things interact. Okay? In the lecture, can you interact with that potential partner? Not quite as well. Okay? In the dinner, you could probably interact with them and find out fairly quickly that that wasn't going to work or it was going to work. Okay? Or have that potential. But in the lecture, you don't get that interaction. So how the reaction happens is very important. What else could we have? Do we get temperature next? We get temperature next, so we can draw that one up. Okay, temperature directly affects the rate. The hotter it is, the more things move. Okay, the more things move, the more interactions we can potentially get. The last one, how else could you possibly get that partner?
They're blind.
Oddly enough, you're using a word that I was going to follow with, but not for that reason. Blind dates? How do you go on a blind date? Random. So you just walk up and say, hey, let's go for a date.
You're outsourcing.
You're what? You're outsourcing. You're outsourcing what?
There we go. Your friends.
You're using your friends. They know somebody, they know you. And they go, I think you guys would be good together. Or, this is going to be an awesome train wreck and I want to watch. Okay? You're using somebody else's advice to make that connection happen. Chemistry does the same thing. We can add another substance to act as the catalyst. And just like in the blind date, the catalyst doesn't get consumed in that reaction. Right? When you go out and have a bad interaction on that blind date and it doesn't work, you don't go back and diss your friend or throw your friend away. You might never take their recommendations again, but you don't get rid of them as a friend. They're still there. Okay? This is effectively what a catalyst is doing. The catalyst helps the reaction happen, but it itself is never consumed across the course of the reaction.
I'm interested. Are we going to be talking more about catalysts or not? So that doesn't really answer my question.
That's a yes.
So that's a no.
Uh,
That's pretty much the end of it. Yeah. Okay. Catalysts are one of the most active areas of research because we want reactions to occur faster. So we always try and develop something to help speed that reaction along. It becomes harder to deal with. It's a huge area of study. And largely what we're doing with catalysts is we're trying to make biological catalysts. Because biology is already doing things that we can't do because they have biological catalysts.
biochemistry.
So we end up trying to mimic those catalytic reactions, sometimes through studying them, sometimes through
Okay. So
trying
do
to
we
mimic
not really
them.
talk about that in organic chemistry?
Not
generally
really.
at all, really?
Definitely doesn't really show up in Gen Chem. We just mentioned that a catalyst does it.
But okay.
And in OChem, we can go through and explain how some catalysts work, but that's about it.
So where was someone about that wanted to learn?
If you wanted to learn about catalysts, you need to go through probably 2.5, 3 years of chemistry
Well, yeah.
and get up to a higher level
So
looking
like
at.
biochemistry and
Biochemistry is largely about studying the biological catalysts, not making them. So you're probably looking at organic chemistry or even inorganic chemistry, them looking at different reagents and how they would force a particular reaction to happen. So your catalyst is effectively like a hammer.
yeah.
Okay. So it's the tool that allows you to do a single reaction. The amount of effort that goes into determining that catalyst is huge. You've
So
now
it's not
built a tool.
necessarily a tangible thing.
Virtually nothing in chemistry is tangible.
Well, yeah, but it's
Yeah.
not like.
Is there a specific class on it? No. You'd probably be looking at that in graduate school. So why talk about equilibrium with acids? If we look at water and the production of H+. So here's H2O. It will dissociate to give you H+ and OH-. That's a plus. Where do you think the equilibrium lies? Reactants or products or right in the middle?
You have more.
Right, if they're right in the middle when we deal with water, half of it becomes H+, the other half becomes hydroxide. Both of those are ions, which means when we test the electrical conductivity of pure water, what do we get?
Zero.
There's ions, which means electrolyte. It should light. Does pure water act as an electrolyte? No. Based on the lab that you guys just went through and tested, water does not act as an electrolyte, which means very little ions, which means where does our equilibrium lie?
For H2O, right?
Way to the left for H2O. because we want a massive concentration of products and a tiny concentration of reactants, okay, based on our own observables. What happens if we say switch to HCl? What can you tell me about HCl? And we'll even add the AQ. It's an acid, which means it forms H plus and chloride ions. How much H plus does it form? Okay. What do you think? If it's an acid, how much H plus do you think we have? A lot. Okay, we should form a lot of it. Otherwise, we wouldn't call it an acid. That's why the name changes. Where does the equilibrium lie now? The other side, heavily towards the products, and we get very little reactants. So when we're talking about equilibrium with acids, really what we're concerned about is where does the equilibrium lie? Okay? Equilibrium can be quantified by products over reactants. What would the K value be for water? Would you expect a big value or a small value?
Big value.
Right? So products divided by reactants. Products are large or small? Small. Reactants are large. Take a small value and divide by a large value. What do you get? A small value. The K, the equilibrium value for water is very, very, very small. 10 to the minus 14. Okay, so powers of 10. If we take a look at HCl, what do we expect for our K value? Very, very big, because our product concentration is huge and our reactant is small. We end up with a very large K value. In that case, again, powers of 10 the other direction, 10 to the first, 10 to the second. Most reactions center on a 10 to the minus 2, 10 to the minus 3 range. Okay, so don't favor all that heavily. Okay? What do we do with this information? This sets us up with strong versus weak. Strong acids will have very large K values. Weak acids will have very small K values. Okay? But that means we'd have to look up these K values, and that's a lot of effort, particularly because they deal with powers of 10. So instead, what we could go through and do is classify our acids as either strong or weak. Strong acids completely ionize in water. That means when they hit water, they become ions. How do I know they become ions? One option is I stick my hand in it and it hurts. Not a particularly good option. Okay, fair, but not a good option because you start losing hands. Okay. Well, we can look at the K value. The K value will be large. That means I'd have to know all the K values. Okay. So instead, what we go through and do is we define certain acids and bases to be strong, and we just say those are strong. What do we say if they aren't one of the strong acids? Those are weak. Okay? So this sets it up with more memorization. You'd have to know the strong acids. I've listed out 6. Depending on the course you go into, or instructors, sometimes they ask for 7 strong acids. The bases, you're looking for hydroxide being bound to a group 1 or 2 cation. It's not perfect, but it gets pretty close.
So that's memorization.
And that's ultimately memorization. As far as this exam goes, you don't need to have that content memorized. It's getting you set up for that knowledge so that you could use it in the future if you wanted. Which gets us the fun concept of safety. Okay, we're talking about the amount of hydrogen ion present. Okay? So if I was trying to save Timmy from a solution that was dangerous, and I could shout out, watch out for the 0.5 molar H plus solution. How many of you knew what molar was before the class started? Not particularly useful. Okay? I could even switch it up to try and say, well, strong acid. Well, how many of you knew what a strong acid was? Okay, so what did you know about acids prior to the class? They're dangerous, but how do we know they were an acid? Nick, in fact, shouted it out earlier, I think.
Where to?
pH.
H,
Okay. Most people have heard of pH. Why have you heard of pH? Acids and bases are dangerous. What we tried to do was convert those numbers into a system that was easier to manipulate. A system that was easier to manipulate because the total range for your pH happens to be 14, less than 20. Why would we want a number that was less than 20? We can't count that high. Okay? This is why we have a dozen. Okay? We literally have small, puny minds. We can't deal with it. So we convert those complex powers of 10 into a pH. Okay? So what we're responsible for knowing is that low and high pHs are bad. The pH right in the middle of 7 is okay. The useful scale that you're probably used to seeing, pH of 0 is strongly acidic, pH of 14 is strongly basic. And everything we consume that's acids or bases falls somewhere within that scale. Typically, we try to avoid the very low end, and we try to avoid the very high end. Okay? How would we get the pH scale?
little sticks.
Sticks. Okay, we could use measurements, use little sticks to measure what the pH was, but that's ultimately coming back to an observation of the hydrogen ion. So what we have here are brackets. Those brackets reference the hydrogen ion concentration, so the amount of hydrogen present. Okay? I take the negative log of that, and I have the pH. Does anybody go like, what?
The natural log of the H.
We've got a log value, which who the hell even understands logs, and a negative value to boot. Okay? That all together converts something really complex, the hydrogen ion concentration, with a complex thing,
So that's
with a
just-
complex thing. So 3 complex things make
That's in
a
just
simple thing.
The negative is just a negative power. So that's you put the power.
Don't manipulate that more than you have to. Okay? And that's how we get the pH. What are you responsible for? Recognizing the scale. Okay? 0 to 14. Okay? And here we're going to be super excited, and we'll reveal why in just a second. What are our electrolytes? Salt is an electrolyte. What is the point of an electrolyte? What does it do? Conducts electricity. It allows for the passage of electrical current. We're looking at electricity or electrons moving through charged ions. So any species that allows for the passage of electrical current is an electrolyte. Okay? A non-electrolyte would not conduct electricity. In that case, there are no ions. So when we go through and look at these, we'd be responsible for being able to identify these as electrolytes or non-electrolytes. Sodium chloride.
It's a salt.
It's a salt, which means
It's an electrolyte.
electrolyte. We'll come back to that definition in a second. H2SO4. If it helps, I could write the AQ. It's an acid, and in fact, if we go back a couple slides, it is a strong acid. What do strong acids do? Completely dissociate into ions, which means we have electrolyte. Sodium hydroxide. Electrolyte, because it's a strong base. Calcium carbonate. Is that a salt? Define salt.
Okay, you did this last time.
Yeah, it's okay. A metal and a nonmetal usually sets us up for a salt pretty nicely. It's an ionic compound. Okay? Is this a metal and a nonmetal? Yes. This is a tricky one. Why is it tricky? Because it's carbonate, actually, yes. What would we have to reference? The solubility rules. And we look at the solubility rules for calcium carbonate. It is a solid. If it is a solid, does it dissolve in water? No, which then means it's not an electrolyte. Iron oxide, same deal. Silver bromide, same deal. None of those dissolve in water. Because they don't dissolve in water, we don't get ions. No ions, no electrolyte. No passage of the electric current. With the last three examples,
Glucose.
I don't know that that's actually glucose. I don't think any of these are glucose. Actually, no, you might be right on that. I was thinking, no, it's not glucose. It might be sucrose. What is different about these compounds than the top six?
We don't know what this is.
What's that?
I'll say three with those ones. Well, four. No, that's
All three of these are
stable sugar.
only nonmetals. If they're only nonmetals, what kind of bond is it?
That's sucrose.
It would be a non-polar covalent or polar covalent. Are any of them ionic? If they aren't ionic, do we form ions? No, which means all three of these are non-electrolytes. Why might this slide be of particular interest to you?
It's the last one.
It is the end. So Thursday will be strictly review. You have the practice final. Go through the practice final. Find the questions that you don't know how to do, okay? So that we can discuss those questions in class and strategies for getting through it.